Nike transforms over 1 billion plastic bottles each year into sneakers that set trends and deliver top performance on any court, street or gym. Imagine stepping into one of their innovation labs. Tables filled with digital sketches transforming into prototypes, screens where engineers measure the flexibility of every fiber in real time, and technicians analyzing the life cycle of new polymers to minimize the carbon footprint. This is where inspiration for every pair of Nikes is born, where creativity and science merge in a constant dance. From the very first steps, Nike's design team dives deep into exhaustive data analysis from both professional athletes and recreational users. They employ motion capture systems to precisely record every phase of a stride: how weight is distributed when the heel strikes, how the toes behave during takeoff, and the pressure variations during sprints or repeated jumps. They also collect biometric metrics, heart rate, foot temperature, and sweat levels, to understand how the mesh interacts with the skin in different environments and under various levels of exertion. All this information feeds into state-of-the-art digital models. Finite element simulations make it possible to visualize fabric deformation and heat dissipation in each area of the shoe. Designers can then pinpoint critical zones where material can be lightened to improve ventilation without sacrificing support, or discreetly reinforce high-stress areas with internal supports that barely add weight. Every line drawn in the virtual sketch serves a specific purpose: strategically placed grooves to channel airflow, contours that optimize anatomical fit, and transition zones with stiffness gradients that follow the foot's natural flex. In the initial prototyping phase, Flyknit fabric takes center stage. Using programmable knitting machines, the shoe's upper is crafted from layers of recycled threads with exact thickness and density, virtually eliminating cutting waste. The result is a piece that molds almost perfectly to the arch and shape of the foot, offering a glove-like fit. Each pass of the computerized needle adjusts thread tension to reinforce high-wear areas while maintaining remarkable lightness, making the shoe feel almost weightless during a run. By combining the precision of digital engineering with the elegance of recycled materials, Nike ensures each prototype meets athletic performance requirements while advancing its sustainability goals. At the same time, recycled PET polyester comes into play to reinforce high-stress areas such as the sides and heel, adding durability without compromising lightness. Flyleather, a synthetic leather made from recycled fibers, brings unexpected elegance, with a feel close to natural leather but with a far more sustainable process. Before any material reaches the cutting line, it undergoes rigorous resistance tests, bending, exposure to extreme temperatures, and stretching to its limits to identify weaknesses that could arise after intensive use. In parallel, life cycle analysis software evaluates water consumption, energy use, and associated emissions, ensuring each component is optimized to reduce its environmental impact. When orders reach the factory, CNC cutting machines start up with surgical precision. Sequences of lasers and automated blades cut each piece with error margins under 1/10 of a millimeter. Flyknit fabric is shaped with almost no waste, while Flyleather, polyester, and other reinforcements are prepped for assembly. Every piece undergoes both visual and automated inspections. High-resolution cameras detect fiber irregularities, thickness variations, or flaws invisible to the human eye. Meanwhile, waste from earlier stages, scraps of rubber and foam, is shredded and reprocessed through Nike grind technology, creating compounds for outsoles and insoles. This way, one shoe's leftovers feed the making of another, closing the loop within the same plant. When the upper and sole are synchronized, the production line takes on a cinematic feel. Picture a row of robotic lasts calibrated with millimetric precision to replicate the anatomy of thousands of different feet, from high arches to more prominent insteps. Over each, the fabric cuts and reinforcements forming the upper are carefully placed, ensuring every layer matches the geometry of the digital design. Next, articulated robotic arms dispense a next-generation adhesive, a two-component polymer that activates under pressure but requires no excessive heat to cure. This method, known as cold bonding, represents a major step forward in energy efficiency. While traditional processes can consume kilowatts of electricity to heat adhesives, this system operates at room temperature, avoiding material deformation and preserving the integrity of ultralight filaments. Once the adhesive is applied, the robotic arms adjust pressure evenly along the bonding surface, holding it for several seconds. During this brief period, built-in force sensors monitor weight distribution in real time, instantly correcting any area with insufficient pressure, ensuring there are no unbonded spots or excess adhesive. While the adhesive sets, high-resolution cameras run sequential inspections to detect bubbles, wrinkles, or misalignments between sole and upper. If the slightest irregularity is found, the system automatically diverts the shoe for reprocessing or recycling, guaranteeing impeccable quality standards. Once bonding is verified, a gentle pulse of mechanical vibration, programmed to mimic the motion of a stride, helps the polymer flow into microspaces, creating a uniform, durable connection. By the end of this step, the shoe not only achieves structural fusion aligned with design specs, but also retains the lightness and flexibility of high-performance materials. Each pair moves down the line, confident that this critical bond will withstand thousands of strides, jumps, and direction changes once on the athlete's foot. Traditional stitching works alongside ultrasonic welding. High-frequency pulses fuse material layers without thread, offering surprising strength while maintaining the essential flexibility for agile movement. Vision systems monitor every centimeter of the bond, correcting anomalies instantly to ensure each shoe matches the exact dimensions prescribed by the digital design. With the basic structure complete, it's time for the sole. Through high-pressure presses and precision molds, a mix of polyurethane, recycled EVA, and Nike grind compounds takes shape, forming traction patterns inspired by nature, leaf prints, fabric-like grooves, or ultrafine textures that enhance grip without adding weight. Before leaving the press, each sole is cooled in thermally controlled chambers, preventing cracks and ensuring the desired hardness. Every sole is laser scanned to measure exact geometry and undergoes dynamic testing. Rotating rollers simulate miles of wear, impact machines repeatedly strike the heel, and traction benches test grip on wet, dry, smooth, or rough surfaces. Only those that pass these trials move forward, the rest are recycled for new processes. Key finishing touches make the difference. Insoles, often unseen, are made with memory foams that respond to heat and foot pressure, molding to its unique shape and offering energy return with each stride. These components are tested in pressure and humidity chambers to ensure they retain their properties under extreme conditions. When all parts come together, each pair undergoes a final quality check, combining human and robotic inspection. Experienced operators assess aesthetics, color, stitching uniformity, logo alignment, while robots test joint strength and midsole flexibility. If all passes, the pair receives a traceability code printed on the inner label, recording the date, production line, and material batch. Packaging is the last link in a value chain that prioritizes both product protection and environmental sustainability. Once the shoes pass all quality checks, they move to packaging, where each pair is placed in boxes made entirely from high-strength recycled cardboard. These boxes, besides ensuring safe transport, are printed with plant-based inks, mainly soy-derived, that provide vivid, lasting colors while eliminating toxic compounds and making the material easier to recycle. Inside each package, alongside the shoes, there's a detailed leaflet explaining best practices to extend their lifespan. It suggests effective cleaning methods without damaging technical fibers, such as using neutral detergents and low-temperature wash cycles, as well as guidelines for air drying and proper storage in ventilated spaces. It also offers advice on assessing shoe condition when wear signs appear and alternatives for repair or refurbishment before disposal. Additionally, spare laces and interchangeable insoles are included, each in biodegradable wrapping. Accompanying these accessories is a small guide with creative reuse ideas, turning boxes into personal organizers or worn insoles into DIY templates, and information on local recycling options in various regions. The aim is to enable a circular economy model. When the shoes reach the end of their life, users have precise instructions to return materials to collection centers, join product take-back programs, or even donate the footwear for extended use. In this way, packaging goes beyond logistics, becoming a key consumer touchpoint that reinforces the brand's commitment to responsible innovation and encourages more mindful consumption habits. Finally, nothing is left to chance. An advanced logistics system optimizes global shipping routes, combining transport modes to minimize carbon footprint. Electric vehicles cover urban routes. High-speed trains and efficient cargo ships deliver orders to distant continents, while AI platforms recalculate the best route in real time in response to unexpected events. When the package leaves the plant, it's no longer just a pair of shoes. It's the result of a process where cutting-edge engineering, inspired design, and a firm commitment to the circular economy converge. Every time you wear them, you carry over half a century of innovation, thousands of hours of research, and the legacy of a company dedicated to turning waste into high-performance gear. It all began in 1964, when Phil Knight and Bill Bowerman joined forces with a clear vision to develop high-performance sports footwear that would make a difference for athletes at all levels. From that small project in Oregon, the company grew step by step, adopting increasingly efficient production processes and strict quality controls. Over time, techniques like cold bonding were introduced to reduce energy consumption, and waste recycling systems were implemented in every plant. Today, Nike not only produces millions of pairs of shoes each year, but also invests in sustainable materials such as recycled polyester and bio-based foams to reduce its environmental footprint. Moreover, the company set clear targets for emissions reduction and responsible water management, measuring progress transparently and reporting annually. Its innovation centers, located on several continents, allow for testing new technologies, from lighter soles to more breathable fabrics, before mass production. In this way, Nike combines global scale with a commitment to resource stewardship. Every assembly line integrates energy-saving protocols and industrial safety measures. What began as the ambition of two entrepreneurs has become a model of conscious manufacturing, where commercial success goes hand in hand with social and environmental responsibility. Electric vehicles cover urban routes, high-speed trains and efficient cargo ships deliver orders to distant continents, while AI platforms recalculate the best route in real time in response to your next.